In this video, we will talk about Homework 6, Problem 1. So given a density function of the intersection of x and y is equal to 1 plus xy over by a, where the absolute value of x and y are less than y and 0 for otherwise. So for the first problem, to find a suitable a, we should let the density function is valid, so which is made on the integral on both x and y. Is equals to 1. So we know now here the definition range is for x and y here, and we know that we can see that x is in -1 to 1 and y is also in -1 to 1. So is the integral on both x and y and for x and y over by a dy to let this equals to 1, which is put the a out. Here. So from this one, it can be applied by 4 over a is equals to 1, which is a equals to 4. And for the second part, find the expected value of x and y is equals to the each x times the density function. So it will be defined range. So it's still both 1 to 1 and x and y times 4 1 plus x and y over 4. So we can also take the of 1 over 4 out and b. And find the integral for from -1 to 1 and -1 to 1 with the function that's xy plus x squared y squared dx and dy. So this solution is equals to 4 over 1 times 4 over 9, which is 1 over 9. To check whether x and y are uncorrelated or not, we need to find the covariance that will be equals to 0, which is the expected value of the intersection is equals to the multiplication of the expected value of x and y. And now we can first we can check for the expected value of x, which is equals to both integral here, the double integral of x times the intersection function of x and y, which is y plus xy over 2, both x, y. And here we can receive a result as 0. Since here is 0, and the expected value for the intersection is 1 over 9, there's no value that can make something times 0 can be something have a value. So which is that that equation is equal, and x and y are uncorrelated. Since they are not uncorrelated, that also means they are correlated. X and y must be dependent. So for the fourth one, we already have we can suppose that the new random variable z is equals to x squared and w equals to y squared, and then the Jacobian matrix for z and w is equals to the partial differential for this one is 2x, and for on y is 0, and here's 0, here's 2y, which we need to use the determinant of the Jacobian matrix. So here it is 2x times 2y minus 0 minus 0 times 0, so which is 4xy. Well, since x and y are both less than 0, the absolute value for x and y is both less than 1 and larger than 0. So for the value of z, the definition range of z and w, they are both in the range of 0 to 1. Then we can replace x and y by z and w be in the determinant of the Jacobian, which is 4 times square root of z and square root of w to receive the absolute value. And since for x and y, their absolute value in this range, but their own self can be negative. So here actually for negative z and negative w has both positive and negative. And so here for z and w will have 4 roots for square root of negative z. So the multiplication for these two have 4 possibilities. As first is square root of z square root of w, which will be both positive, and second one is negative square root of 0 square root of w, and third one is square root of 0 negative square root of w, and the fourth one negative square root of z and negative w, square root of w for both x and y. Now we have actually 4 different kinds of solutions. So we may need I equals to 1, 2, 3, 4. So now we can find the density function of z and w by each steps as fxy divided by the determinant on J1 and plus fx over J2, the summation here at the same time. And now all this can be take out since they actually both are for square root of z and square root of w over 1, and times we can replace the x and y before to square 4 different kinds of the solution by x and y in the original intersection value function as for 1 times by 1 plus square root of z square root of w minus plus 1 minus z w square root of z square w and replace them all together. So here actually we can receive a result of the solutions here. Both can be delta 90 and here is 4. So here we only have 1. And so the final result is 1 over 4 times square root of ZW. And now we have the function. Here is for the Z and W are both in 0 and 1, and for 0 in otherwise. For the fifth one, we can check. Now here we have the intersection of the density function of Z and W. We just need to check the density function of Fz and Fw on both definition range. So here, for Z is equal to from 0 to 1 times we can separate we can split 4 times 4 to the 1 over 4 to the square root of ZW into these two parts as for easy computation, and then take the integral on W to find the Z, which is 1 over 2 square root of Z. And for Fw, we have the same way to calculate, which is 2 to the W. And so we can obviously see that ZW is equal to the density function of Z times the density function of W. And now we can imply that Z and W are independent, which is x squared, the original x squared and y squared. These two random variables are independent.